So, hello everyone, and today I think is the last session for this NPTEL course. And today we will not be solving any problems. We will be just discussing what we have, studied in all these weeks and what is like what basically have we done in this course of fluid mechanics. Okay, so that that is the basic what we have studied in all these, I think, 12 weeks or so of total coursework. So we'll discuss what we have basically done, and I think that will be very helpful, right? So first, we in the first module or in the first week, we discussed about some introduction to fluid mechanics, how fluid mechanics and all started, and who are all the scientists who gave different ideas. And then we studied about different types of, you know what are the different types of equipments or where fluid mechanics can come into use, right? So these are all what we studied in the first lecture. uh, then in second lecture, we studied about what are the characteristics of a fluid, like what does fluid basically mean, like, so, and what are the different types: gases, liquids, what is an ideal gas, what is a perfect fluid. And then we studied about the Newton's law of viscosity, which is a very important correlation between shear stress and the velocity gradient. We discussed about Newtonian fluid and non-Newtonian fluid. Then we discussed about some of the properties like density, viscosity, specific gravity, API gravity, specific volume, and many more. Right. We also, discussed about properties like surface tension, capillarity, bulk modulus, compressibility. These all things we have discussed. Then we also discussed about the characteristics of a, you know, ideal gas like PV equal to nRT or PV equal to RT equation that is useful for describing the ideal gas, and at what conditions we can assume a gas to be a ideal gas. Then in the third lecture, we studied about fluid statics. That is, what do you mean by statics? So overall, there is a balance of forces, and what are the forces that can act on a body? Like we have surface forces, body forces. In surface forces, we have pressure. Sorry, in uh, body forces, we have gravity, right? And surface forces, we have shear stress, and we have surface tension, other forces, right? Then we, discussed about the three characteristics of fluid. That means the pressure of a fluid always acts perpendicular to the contact area, and In regardless of the direction, also the pressure will remain uniform. And we have also studied about the Pascal's law and concept of hydraulic press. And we have also studied about pressure at a particular height is equal to rho g h. That expression also we have studied. We studied about absolute pressure, gauge pressure, vacuum pressure, and many more pressure measuring instruments also, right? And pressure measuring instruments can be manometer, micromanometer, pressure gauge, pressure transducer, and others, right? And then we studied about the pressure that is acting on a plate, the concept of centroid, right? And also concept of floating bodies like buoyancy and metacentric height, and all these concepts. Also in metacentric height and pressure relation, we studied about equi-accelerated motion, and also in case of rotational motion, how we can define the we can write the expression for the expression for uh, height that we get when it is circulated or the cylindrical vessel is rotated at some constant angular velocity. What is the expression, or how the height changes with respect to r? That expression also we derive. And then we studied about the you know fundamentals of uh, flow, like concepts related to Lagrangian method, Eulerian method. So Lagrangian method is when we observe a particle and we see fluid how it particle moves from one point to another, and what like when it moves from one point to another, how the different properties changes. And in Eulerian approach, we fix a particular location in space, and then we observe the change that happened in that particular location. Then we understood the concepts of streamlines, like what are streamlines, what are the expression for streamlines. Then we studied about stream functions and their expression for stream function. Then we studied about stream tube and tube filament, I guess, and other kind of flow representative lines like streak lines and path lines, timelines, potential lines, velocity potential concepts, flow net, and many other, right? And then we discussed about different types of fluid flow, and that is, when we encounter any situation, what we do is to simplify the problem so that we can use the known equations to solve and get an analytical solution. So, what are the different specific cases that we studied are steady state flow, steady and unsteady flow, uniform, non-uniform flow, develop compressible or incompressible flow, viscous and inviscid flows, laminar flow and turbulent flow, one, two, and three dimensional flow, rotational and irrotational flows, subcritical, supercritical, subsonic, supersonic, all this, and sonic flows. Correct. And then we also discussed about some fundamental aspects like what do you mean by a system, what is the control volume, control surface, so that we it will help you in analysis of or deriving the equations for this kind of flow arrangements, right? And from here, we also discussed about acceleration and what is the local acceleration, what is the convective acceleration, and how we can get expression how this concept of substantial derivative is different from a uh, local derivative or a simple derivative, how this substantial derivative is different. Then we also discussed about the angular velocity concept, then vorticity, and how vorticity is related to the angular velocity. Then we studied about the Stokes theorem on circulation. This is what we all studied in the basics or fundamentals of flow. Right. So this is, I think, up to lecture 6. So I'll give you 5 minutes. If you look at all those things, and then we will continue our discussion again. Okay. Okay, so let us see next what we have. And next, then we studied about the basic one dimensional flow, like the basic fluid flow equation, conservation of mass, from where we obtain the continuity expression or continuity equation for one dimensional, two dimension, and three dimensions. And then we solve, questions on the continuity equation, and we derive the Bernoulli's equation for uniform flow. Then we obtained the energy equation. And also we saw how we can modify the equation in case of laminar flow and turbulent flow. And we have given a parameter alpha to the kinetic head. We obtain alpha times of v square by 2g, where we so that we can this overcome or surpass this assumption of uniform flow and use it in different types of flow conditions. Then we studied about the momentum equation and how this uh, what kind of force in case of what kind of force a fluid will be exerting on moving fluid will be exerting on a flat plate or during a sudden change in direction. So for that we studied about the momentum equation, and from there we studied about the loss in sudden expansion, right, and loss in contraction, and all these things we have studied. And we also studied about the propeller and the water from wheel pump and others. Then we studied about the viscous flow, the flow of viscous fluid, for which we derived the, I think, expression for Navier-Stokes equation, right? That was, I think, one complete lecture that we have taken for the derivation of the Navier-Stokes equation. And as we know, this Navier-Stokes equation can be written in three coordinate systems. One is a Cartesian coordinate system, one is cylindrical coordinate system, and one is a spherical coordinate system. But in most of the cases, these equations will be given to you in your exams, and you can simplify it according to your requirement of your question, and then you can solve it. Okay. So you don't have to remember the entire equation. The specific part or the entire equation will be given to you. Okay. And then we studied how what will be the equation for laminar flow in such a case, and we got a simple equation or a simple parabolic profile for such kind of laminar fully developed flow profile. Then we studied about Couette flow and also obtained expression for Couette flows, both in cylindrical, I think in Cartesian coordinate systems, right? And also we obtain expression for flow in circular pipes using cylindrical coordinate systems. And then we studied about the part where we have turbulent flow, right? Because the flow will not always be turbulent, as we know from the Reynolds number that the flow can be laminar, transitional, and then turbulent. And in turbulent flow, we studied about the magnitude of turbulence, intensity of turbulence, and what is the total shear that the fluid will be experiencing will be because of the eddy viscosity and the viscous stress, the laminar shear stress plus the eddy shear stress. Both of them will be acting, and from there we can get a relationship that total stress is equal to sum of individual viscosity times of the velocity gradient. And then we obtain expression for smooth pipes and universal velocity profile for such turbulent flows. After that, we looked into different types of losses in pipe. We have frictional losses, and for that we have studied about the Darcy's Weisbach and Fanning equations, and Darcy's Weisbach friction factor, Fanning's friction factor. These different types of friction factors we have studied. We have obtained the general expression, and from there also we have obtained this specific expression how we can we related that okay, this will be the value of the friction factor, that is 64 by Re for different types of cases that we have obtained. We have also obtained you know different correlations for obtaining this friction factor for different kinds of conditions. Like we have studied about the cool Colebrook 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 expression. Then we have studied about the Blasius equation and Moody's empirical equation also studied. And Moody's chart is something that is more important. That also we have discussed. And also we looked into factors affecting head losses. Head loss can be of you know uh, different types of head loss, minor, major losses, and how we have different values for K, for which we can modify, or different loss in head in bends, losses in elbows, uh, T, if we have a T junction, how the losses will be, and different empirical equations also we have. Uh, Also, sometimes these flow channels will not be circular. In such a case, we have introduced a concept of hydraulic mean diameter. So, hydraulic mean diameter is a important concept, which is nothing but four times the cross sectional area by wall perimeter in contact with fluid. So, that is also one important concept to remember. And after that, we have studied about, you know, different losses. We have studied about different types of valves like gate valves, globe valves, butterfly valve, and what would be the total loss in a pipe. And we have studied about pumping, pump action of pump, and what is the total head generated and how we can use, and what is the efficiency a pump and a pump can give, and also the total head and load characteristics of pumps. So that is what we have studied up until I think lecture 17, right? So again, I'll give you 5 minutes to think about, to remember about all these things, and then we will again take a. I'll give you 5 minutes, and then again we will move on into next section what we have studied. Okay. Okay, so let us continue again, right? So from after that, we studied about flow in water channels, and we have seen how it is different from regular channels, and then we studied about water channel cross section and which cross section gives the maximum flow rate. That we also studied. We obtained and studied the equation of specific energy, and for constant discharge, how we obtain the critical situations, right? Critical situation also we have studied. Yes, we studied about the subcritical and supercritical flows, and up to what height for a specific height we will be having different types of flow regimes like supercritical, subcritical flows, and that also we have studied. And then we studied about the wave velocity during this uh, to obtain the wave velocity, critical velocity. Then we studied the concept of hydraulic jump and analogy between hydraulic jump and the shock wave. That also look right. Then we looked into this drag, effect of drag, lift, and cavitation. Like in drag, we first studied that how the flow occurs around the body, what is the concept of stagnation pressure, and we understood, we realized what is drag and how drag is generated. And then we obtained the expression for drag and saw how for different kinds of bodies, like streamlined bodies, how drag is different, right? Then we obtained a general expression of drag, and we also looked into something called D'Alembert's paradox. So that also we studied. We obtained the pressure difference or the like with change in angle, how the pressure difference changes. That also we did. Then we saw how for for cylindrical body with increase in Reynolds number, how the change of flow or the angle at which flow separation occurs changes. That is also something that we looked into. And we also studied about the frequency of vortex formation. We looked into this von Karman for, von Karman, vortex street, and like I think for some value of Reynolds number, it will show a alternate flow pattern, right? So that also we look. And also we looked into some of the expressions like how to obtain this drag coefficient, and also over a flat plate how this effect of boundary layer, because of this boundary layer, how what kind of drag can experience, that also have studied. Then we looked into some concepts of lift, uh, how lift is generated, the lift force, how it is generated, and like what kind of design and what kind of angle of attack we should have so that we can generate sufficient lift, and all these things that we have seen. We have also looked into this concept of cavitation, like how cavitation occurs and how to minimize this extent of cavitation, other things that also we did. Then we studied about the dimensional analysis. In dimensional analysis, we studied main analysis, two major methods to do analysis. One is the uh, Buckingham's pi theorem, I think, and another is the Rayleigh method. Right? First, we studied about the Rayleigh method, and then we studied about the Buckingham's pi theorem. In both of them can be used for dimensional analysis. And I think you remember in a Rayleigh method, what we do, we write it in some form of like y is some function of x, y, z to the power of some constants, and then we equate both the sides, the dimensions of both the sides, and then obtain the unknown constants. Similarly, in Buckingham's pi theorem, we create dimensionless groups, and then we introduce some relation between them using those dimensionless groups. And then we looked into this concept of similarity or similitude. We have geometric similarity, kinematic similarity, dynamic similarity. So for so these similarities are introduced so that we can scale up the existing. If we have a kind of a model system, and from there we want to build a prototype. So for that, in that case, how we how we can scale the system without any changes or acquiring the same output, how we can design the system so that we get the same output in the prototype. So for that we have this all these similarity relations. And also we have studied about some dimensionless numbers like Reynolds number, Froude number, Weber number, so the Mach number. These are all useful for such kind of similitude analysis, right? So this is all we studied about the dimensionless analysis and similitude. Then we looked into some basic concepts of compressible flow. Like we know that flow can be compressible. So in compressible flow, where we observe this compressible flow and how we obtain this expression for compressible flow, we studied about Mach number, and we also obtain the energy equation in case of this compressible flow. Also, we studied about this isentropic flow conditions and effect of change in cross section for this compressible flow. And we have also looked into this choke flow condition and convergent divergent nozzles and other things. Also, we have studied and about shock wave, how shock is generated, oblique shock. Also, we looked into Fano flow, Rayleigh flow, all these situations also we looked into. These are also some like from those expressions, continuity, momentum, and energy equations for compressible flow, we can obtain all these expressions. So also we looked into critical velocity and critical pressure for maximum flow rate, because one choke flow occurs, that is the maximum flow rate that we can get. So that also we have studied, we have seen. And also for this energy equation also we know that how it is different that from the regular Bernoulli equation. We know we have another introduce another term of k by k minus 1. K is the isentropic constant term, and then we can use that equation, right? So again, I'll give you 5 minutes to think about all these regions, all these sections, and then we'll discuss about the next part that we have left with. I think we left with very less part, I think, right? So you think about it for 5 minutes, and then again we'll continue discussing. Okay, so let us continue our discussion. What is left? Okay, we have discussed about compressible flow, and what we are left out with, I think, some flow measuring devices, flow measurement devices, and in this flow measurement devices, we have first described different flow measurement devices based on flow classification. Like for open channel flow, we use different kinds of devices. Closed bounded flow, we have different devices, and like we have also on basic principle of flow measurement, we have divided the flow measurement devices into different types. Like differential flow meters, variable area flow meter, positive displacement flow meters, mass flow meters, and then open channel flow meters. In open channel flow meters, we have wires, flumes, subburst orifices, current meters, acoustic flow meters, and many more. And in these flow measurement devices, we studied about venturimeter, flow nozzles, pitot tube, orifice meters, right? And we obtained the expression for venturimeter, and we studied about the uh, pressure recovery yes, of venturimeter, advantages and disadvantages of venturimeter, pitot tube, Prandtl tube, and uh, and all of them have different advantages and disadvantages, and where to use what kind of devices that also we have discussed. We also looked into this principle of Bernoulli's equation, E liquid jet, that also we studied, and then we studied other types of flow meters uh, apart from all this, like based on variable area flow meters, we have rotameter, turbine meters that also we looked into. And other flow meters are also there on positive displacement flow meters like rotating disc flow meter, rotating vane flow meter, load impeller flow meters. And also we have vortex flow meters, electromagnetic flow meters, ultrasonic Doppler flow meters, thermal flow meters, Coriolis flow meters, fluidic flow meters, and then open channel flow meters. We look into all these concepts, right? What are the different concepts? For example, in vortex flow meters, we used this von Karman effect of vortex shedding, and then we obtained this expression. We looked into this Strohan number, how it is related. And in thermal flow meters, we have two types of uh, basic concepts. One is we keep the power constant, and one is the temperature difference constant. So in both of these approaches can be used to measure the flow in a particular fluid medium, right? And then finally we looked into I think something called multi-phase flow. Like when we have different kinds of like more than one kind of phase that is involved. In such a situation, how to obtain different condition for like how do we analyze such systems is what we studied in multi-phase flow, where we studied about this bubble flow, annular flow, plug flow, and also different concepts like what is the superficial velocity, slip velocity, bulk density, bulk viscosity, and other things. And that is, I think, the last module for this fluid flow. So these are all the concepts that we have discussed in this operation of the fluid flow operation course. And I think you have studied all this and prepared well for your exams. Just look into whatever questions that have been done, look into all the assignments that has been done, look into all the extra MCQ questions that we have discussed, and I have uploaded them in the drive as well, so you can look the equations from there and just go through all these equations. I think it will not be very difficult. So one thing we can do is now one thing we can do is we can take one random question, then try to solve it so that, and then we can end the session. Right? Let's see. Yes, you can try this question. You can give it a try, and then we'll discuss about the solution, and then we will end the session. Okay. Okay, so let's see. I think this question we have already discussed. So this is the continuity equation in cylindrical coordinate system, and you can cancel all the terms as you can see. And because of all these assumptions that we will be considering, and then we will end up with this equation. And you can solve this equation to get a very so you can solve this equation to get this v theta is equal to c1 times of r divided by 2 plus c by r. And these are the boundary conditions which you can put to finally find c1 and c2. And then you can substitute these values to get this expression for tau r theta. So this is something that we have already done. So let me take another question. Let's try this. So try this and then we discuss. So let us see. I think this is also we have something that we have done. So this is the continuity equation. We will be substituting u, and then from here we will be imposing the no slip boundary condition at the wall, and then we can obtain the value of v, right? So I think this is what we will be discussing for today, and you practice all the questions, and then all the best for your exams. And I think this is today's the last session, and thank you all for joining this, taking this fluid flow operation course, and to give your reviews in the session review forms. Okay, so all the best, and uh, practice more questions, and all the best for your exams. Okay.